So it's my pleasure now to introduce Emilija Dzuverovic from Venice, who's going to speak to us about rotational to scalar invariance. So Emilia, the floor is yours.
Yeah, so good afternoon, everyone. I'm Emilija Dzuverovic from the Ca' Foscari University of Venice. Today, I'm here to present the paper entitled From Rotational to Scalar Invariance, Enhancing Identifiability in Score-Driven Factor Models, reflecting the work in the collaboration with Giuseppe Buccheri from the University of Verona and Fulvia Corsi from the University of Pisa. So let us start from the very beginning by pointing out that given the increasing interconnectedness of the global economy, the dynamics of a panel of the financial and/or economic time series can often be described by a set of few common factors. For this reason, the adoption of factor models has become increasingly popular in the econometric literature. Within this framework, the common factors may be either observable or latent. Obviously, an assumption of latent factors is less restrictive as it sidesteps the challenge of selecting the common factors from a vast array of potential explanatory variables. In addition, it enables the factors to be extracted based only on the available data. However, the use of unobservable factors generates identification issues, the solution of which poses significant interpretability problems. For instance, the estimated factors may be either order-dependent or defined up to rotations, terribly complicating their economic or financial interpretation. In this regard, via this paper, we contribute along different directions to the literature on the so-called score-driven factor models. In these models, the factor dynamics are driven by the score of the conditional observation density. This implies that the main source of variation of factor dynamics are available observations. It follows that the main advantage of these models with respect to competing parameter-driven specifications that we will introduce shortly is that the likelihood can always be written in closed form. Moreover, the law of motion of factors, being driven by the score of the observation's density, is naturally robust to extreme observations which may occur during periods of the financial and/or economic turbulence. In this regard, the first contribution of the paper is the new identification scheme, showing that score-driven factor models can be identified under significantly milder restrictions compared to parameter-driven factor models. The second contribution is to show that this identification scheme can be used in score-driven factor models with dynamic loadings and in nonlinear factor models. So we start by illustrating different behavior of parameter-driven versus score-driven models when scaling the factors through a non-singular square matrix denoted by capital T. Let us first consider the following parameter-driven factor model, where y t is an n by 1 vector, alpha t is a vector of unobservable common factors.
Emilia, I'm sorry. I think
Yeah.
we're stuck on your first slide.
Oh, sorry. I don't understand why. And now?
Maybe stop sharing and share again.
Okay, yes, sure. Okay, let's try this way.
Yes. Try scrolling between slides, just real quick.
Now?
Yes, fantastic.
Yeah,
Fantastic.
okay.
Please go ahead.
So we first consider parameter-driven factor model where y t is an n by 1 vector, alpha t is a vector of unobservable common factors, and capital lambda is an n by r matrix of factor loadings. The two white noises, epsilon t and eta t, are independent. Let us further introduce the non-singular square matrix capital T. It follows that the above model is reparametrized according to the following specification, that basically shows that the two parametrizations are observationally equivalent. Hence, the model is not identifiable without imposing prior restrictions. Specifically, we need R-squared restrictions, where R denotes the number of latent factors, which is indeed equal to the number of degrees of freedom of the matrix capital T in order to fully identify model parameters. In this regard, a common identification strategy consists of restricting the covariance matrix of alpha t or that of eta t to be the identity matrix. This leaves the factors identifiable up to an orthogonal transformation. We thus need to fix the remaining r multiplied by r minus 1 over 2 free parameters. That is, we need to specify the particular rotation being estimated. This is typically done by imposing certain structure on the factor loading matrix. Several types of restrictions have been exploited, some of which are order invariant, while others depend on the ordering of the variables. So let us now define the information filtration generated by the process Yt. The score-driven factor model is given by the following specification, where again, epsilon t is a white noise with covariance capital sigma, C is an r by 1 vector of constant terms, capital A and B are the r by r coefficient matrices, St is the scaled score of predictive log density with respect to the vector Ft, and capital St is an r by r scaling matrix. In practical terms, the updating equation uses the score function of predictive likelihood contribution at time t as its driving mechanism. From the perspective of the optimization, the time-varying parameter Ft plus 1 is updated in the direction of the steepest increase of predictive likelihood at time t. A typical specification of the scaling matrix, capital St, is given by the following expression, where within parentheses we have a conditional Fisher information matrix and the power beta is a scalar set between 0 and 1. For example, if beta is different from 0, then the score is corrected for the local curvature of predictive density, and it also ensures that the scaled score has a finite covariance matrix. But let us now consider again a non-singular square matrix, capital T, and reparameterize the loading matrix and vector of factors accordingly. In the paper, it is shown that the score-driven factor model is reparameterized according to the following specification that shows that the dynamics of the transform process Ft cannot be written as the standard score-driven recursion of the form given previously. In fact, this is because these two matrices do not generally commute, preventing the latter term from being absorbed into the reparameterized matrix A that multiplies the scaled score. Therefore, score-driven factor models behave differently compared to parameter-driven factor models, where for any choice of the matrix capital T, transform factors follow the same linear process describing original factors. Indeed, it is straightforward to show that among all of the possible values of beta from 0 to 1, there exists only two specific values for which this term can be absorbed into the reparameterized matrix A for any choice of the matrix capital T. Specifically, beta is equal exactly to 0 or 1. Score-driven factor models are subject to the same identification issues of parameter-driven factor models, since multiplying the factors by an arbitrary non-singular square matrix results in a recursion of similar form. To the best of our knowledge, the only work so far addressing the identifiability of score-driven factor models is Artemova, introducing the identification scheme for the case when the exponent beta is equal to 1, obviously subject to restrictions imposed on the loading matrix, coupled with special maximum likelihood algorithm for the model estimation. But let us now consider the case where beta is between 0 and 1. For instance, we may set it equal to 1/2, meaning that the score is scaled by an inverse square root of the conditional Fisher information. Indeed, this normalization is quite common in score-driven specifications. Obviously, the resulting equation for factors has a different structure compared to original factor dynamics shown below. As such, we use this result to identify static parameters under much milder restrictions compared to those required in parameter-driven models. Specifically, these restrictions ensure that these two matrices do not commute, so that the latter cannot be absorbed into the reparametrized matrix A. And to do so, we make the following assumptions. First, the matrix A is diagonal with non-zero diagonal elements. Second, the conditional Fisher information is not block diagonal. Well, the restriction in assumption 1 is very common in score-driven literature. The assumption 2 is generally verified if the loading matrix and or the covariance matrix are unconstrained. Finally, we prove the following theorem that shows that when the score is scaled through an inverse square root of the conditional Fisher information, among others, the static parameters and common factors are identifiable up to a common multiplicative scalar term under fairly general assumptions imposed on the structure of the parameter space. Compared to parameter-driven factor models, where restricting the covariance of factors to be the identity matrix leaves them defined up to rotations, here restricting the matrix A to be diagonal identifies static parameters and factors up to a common multiplicative scalar constant, thus avoiding rotational invariance. Clearly, this improves the interpretability of the model estimates because the impact of the common multiplicative scalar term is only to scale the factor dynamics. In this regard, to remove the indeterminacy associated with the scalar factor, we need to fix one parameter. Specifically, we may fix one of the entries of the loading matrix or of the vector of constant terms. The latter choice is more convenient as it leads to order invariant restrictions. As such, we set C1 equal to 1 implying Q equals 1. As a consequence of our theorem, all the static parameters are identifiable. Moreover, the order of the time series within the cross-section is irrelevant because the rows of the loading matrix can be permuted without modifying the likelihood. In the paper, we prove that this result holds for a wide class of elliptical distributions such as multivariate normals, student, so on and so forth. So now we proceed to briefly discuss an important property of the score-driven and in general time series models, which is invertibility. In fact, it can be shown that the choice of a different exponent beta has implications on the asymptotic behavior of the scaled score norm. Specifically, the latter grows faster with increasing cross-section dimension at declining beta that may have implications on the model invertibility. But we show that this can be avoided by simply redefining the scaling matrix as indicated, where this new scaling factor restores the same asymptotic behavior of the scaled score norm as it is the case when the exponent beta is equal to 1. In particular, this adjustment guarantees that the scaled score norm has the slowest growth rate, as it is the case when beta is equal to 1, but at the same time preserves the identification of model parameters up to a common multiplicative scalar term. So, for the purpose of being finally in time, I will only point out that we prove by analogous assumptions that the identification of model parameters up to a common multiplicative scalar term applies also in a dynamic setting with time-varying loadings and in score-driven non-linear factor models. As follows, we have initially performed an extensive Monte Carlo simulation analysis in order to demonstrate that the model is identifiable under a discussed scalar restriction. To this end, we have studied the finite sample properties of the maximum likelihood estimator in both constant and time-varying loading cases, showing that the distribution of the estimator concentrates around true values as the sample size increases in all cases and in all settings. And now the main goal of our empirical application is to show the flexibility of the introduced identification scheme to capture dynamics of both financial and macroeconomic time series. To this end, we apply the proposed framework to two data sets, a panel of 8 macrofinancial time series previously used in the literature to extract economic activity indicators, and the daily return series of 87 constituents of the S&P 500 index. In both cases, we compare the benchmark score-driven factor model with a set of specifications with restricted loading matrix. Specifically, we initially consider a common restriction from the earlier literature to ensure the identifiability of model parameters. In this regard, the LOA triangular structure is imposed on the first rows of the loading matrix corresponding to the number of latent factors, with diagonal entries set equal to 1. In this case, fixing the parameter C1, that is the first entry of the vector of constant terms, is not required for the identification. Indeed, we label this restriction as the general LOA triangular subsequently. Then we examine loading structures in score-driven factor copula models of offshore encounters. They divide the assets into groups according to their industry classification, assuming that all the assets within groups share the analogous dependence structure. So without...
Emilia, sorry,
Yeah?
4 minutes.
Okay, perfect. So in the first part of the empirical analysis, we show that the models with unrestricted loadings always significantly outperform each of the corresponding lower triangular restrictions. And we also show the robustness of the estimated factor dynamics with respect to the changes in the ordering of the observed variables. Then, in the second part of the empirical application, we confirm that the models with restricted loadings are always inferior with respect to the corresponding model with unrestricted loading matrix, that is the one with the same number of latent factors, with the best fit among the former, achieved under the general LOA triangular restriction. Hence, reducing the model complexity by grouping the data based on the observed characteristics, such as the industry classification, significantly reduces the model fitting. We then extend our analysis in order to incorporate score-driven factor models with dynamic loadings, where we essentially reach the analogous conclusions. So, to briefly wrap up, this paper studies the identifiability of score-driven factor models, demonstrating that under fairly general assumptions imposed on the structure of the parameter space, the static and time-varying parameters are identifiable up to a common multiplicative scalar term. This property distinguishes them from parameter-driven factor models, which are identifiable up to rotations. And it follows that the ability to identify score-driven factor models more precisely under minimal restrictions enhances their economic interpretability. We then extend our results to incorporate score-driven factor models with dynamic loadings and non-linear factor models. Ultimately, we validated theoretical findings using both simulated and empirical data. So thanks a lot everyone for the attention, while any potential question, suggestion or feedback is highly welcome.